Hello everyone, thank you for having me. This video is called Design of a Grid-Connected PV System with Net Metering. If you missed our previous video, I recommend you go back and watch the earlier ones to get a good foundation as they discuss a lot of things in more details. So, in this video, we will talk about some exercises about designing a grid-connected PV system with net metering. Before starting, let's talk a little bit about the so-called net metering. So here, in a grid connected PV system, we have a lot of components. We have the solar panels connected together, the inverter for converting DC current to AC current. We have the load, and also we have the grid connected or the electrical grid connected. And between we have the net metering to measure either electricity produced or electricity consumed by the load. The so-called net metering or net meter means when your energy use is higher than your solar panel production, for example, at night or during cloudy days. So you will pull electricity back from the grid, running your meter forward. Yes? So this is a consumption of energy. So at the end of the month or the year, you will be billed the net amount of what you send to the grid and what you pull from the grid. If you inject your produced energy sometime, if your production is higher than your consumption, you will fit your energy into the grid. And if you consume from the grid, so the net metering means that you can be paid from the integration of electrical energy integrated into the grid. This, of course, this policy is not applied in all countries. It's just applied in some countries, or not applied totally. Sometimes we can find that some country applied this partially. Okay, so by the end of this video, we'll be able to design the so-called PV system with net metering. Of course, designing the number of panels, design the inverter, and also to calculate the amount of energy you can sell to the electricity grid. Okay, let's switch to the statement of the exercises. Okay, this exercises involve the design of a grid-connected PV system with net metering for a residential building. The objective is to calculate the necessary components, including the PV array, inverter, and other equipment to meet the building daily energy consumption of about 30 kilowatt hour. So let's say that the assumption of the consumed energy during the day is about 30 kilowatt hour. The system will utilize 350 watt solar panels. Okay, this is the recommendation of the exercises with an assumption of 10 kilowatt hour per square meter per day. Okay, this is the sun power per day, about 5 peak sun hours per day. Additionally, in these exercises, we will talk about the evaluation of some KPI, performance indicator, like the payback period and the return of investment. Okay, this is the questions. The first question is what is the total energy or annual energy demand of the building? Okay, we will calculate from the data given in this exercises. Calculate, of course, the size of PV array. So calculate the number of panels. Okay, we have the individual power of each PV module. Then calculate the inventor capacity. In the question number 5, we will talk about the net metering statement. Okay, then we will talk about the cost of the system, giving some assumption of the costs of panels, of inventor, and the installation costs to get an overview about the total cost of the PV plant. Then we will calculate the electricity tariff and energy produced by the PV system with estimating, for example, that we can buy the electricity with about $0.12 per kilowatt hour. And finally, we will calculate the KPI, especially the payback period of the PV system. After this introduction of the exercise, let's start with the first question. The first question is, what is the total energy demand or annual energy demand for the building? So based on the daily energy demand, we will calculate, of course, the annual. The second one is to calculate the size of PV panel needed to meet the energy demand based on the available sunlight power. Okay, let's switch to the first answer. The first answer about the energy or annual energy consumption, we have the daily energy consumption of about 3 or 30 kilowatt hour per day. Okay, so the annual energy demand is 30 kilowatt hour per day time the number of days. 365 equal about 10 megawatt hour per year, or 10,950 kilowatt hour per year. Okay, so the second question is to design and to calculate the PV array size, okay, based on the available radiation. Okay, it's also very simple. We have, of course, the available radiation of 5 hours means 5 kilowatt hour per square meter per day. Okay, so to calculate the output power of the PV system that we should install, it's very simple, just to divide the daily consumption by the available sun hours or sunlight. Okay, let's give about 6 kilowatt power that we have to install. Okay, for the third question, okay, the third question is, how many panels are required to meet the PV array size? In the calculated or in the previous question, we have, of course, the utilized solar power. The solar power will be of about 350 watts. Okay, and the total energy demand is about 6 kilowatt hour. So the number of panels is to divide, okay, the total output power of the system is about 6 kilowatts divided by the output power of each module, which is, of course, 350 watts. It gives about 17.14 panels. So we can measure it to take 18 panels. Okay, so the number of panels is about 18 panels. For the next question, what is the required inventor capacity to handle the total energy produced by the PV array? Okay, so generally, the capacity of the inverter is about the round of the capacity of the PV system. Okay, we can of course sometimes measure it was about 10% of the capacity of the PV panel. So generally, in this exercises, we will take the same power of the PV system or the PV array. Okay, let's take the inverter power of 6 kilowatts. Okay, here in the question number 5, we'll talk about the net metering. Assume the building remains connected to the grid under a net metering arrangement. If the PV system generates excess electricity during the day, which is sent back to the grid, and the grid supplies electricity at night when solar generation stops. Okay? The first question, calculate the impact of net metering on the annual energy consumption if 60% of generated energy is consumed directly by the residential installation or the residential load, while the remaining 40% is fed into the grid. Okay, so the response of this question is as follows. Here we'll discuss the scenarios of the net metering. So we have calculated the total energy generated by the system. We found about 10.9 megawatt hour per year, okay, or 10,900 kilowatt hour per year. So in the question we have two values. The first one is 60% of the generated energy is consumed directly, and the remaining is about 40% is injected or fed into the grid. So here we will calculate the percentage of energy consumed directly will be about 6. Okay, will be about 6,500 kilowatt hour per year. Okay, will be consumed directly by the residential load, and the rest of about 40% will be injected into the grid. Okay, this value will be injected into the grid. Okay, this is the so-called net metering. Okay, is there any question? Okay. For the next question, how does net metering reduce the need for external electricity from the grid over the year? As calculated here, we can find that with the net metering, the energy fed back to the grid will offset the building's energy needs during no solar hours or no solar hour. As a result, the need for external electricity from the grid is reduced by the amount of energy fed into the grid. Okay, for example, if we produce extra energy, we will inject this energy into the grid when there is no sunny, there is cloudy days. Okay, we will consume from the grid, and with the net metering we can calculate the difference, okay, to use the energy stored into the grid locally. The next question, based on the electricity tariffs and energy produced by the PV system, what are the estimated annual saving with net metering? Assuming that this is the tariff of kilowatt hour. 1 kilowatt hour or the price of 1 kilowatt hour is about $0.12. Okay, so okay, we have this question number 6 before the question number 7 is to estimate the total cost of the system. Okay, sorry. So let's start with the first question. The total energy cost. So we have to calculate the cost of solar panels, the cost of the inventors, okay, the cost of cabling, etc., and the cost of installation. Let's just give a simple calculation of the cost of panels, cost on inventors, and cost of the installation. Let's assume that the cost per panel of 350 watt is about $150. Okay, it's about this price. The cost of all panels together is 18 times the price of each panel. It's about $2,700. Okay, the inventor cost is about $1,500. And finally, the installation cost is about the installation cost means the cost to make to connect the different panel together, and also to make the PV system operating correctly. So the total cost is the sum of the three costs: cost of solar panels, 18 panels, the cost of the inventor, and the cost of the installation. That gives about $6,200. Okay. For more information about the cost of the different components, you can take a look on this website. Here you can find a lot of information about the prices of the different components, about the prices of panels, the prices of the inventor with different manufacturing, different characteristic, different category or technology. Okay. So actually we can switch to the question number 7. As I told, let's assume that the kilowatt hour, or the price of 1 kilowatt hour, is $0.12. Okay. So the annual saving with net metering is about 40%, which we have already calculated. Okay, this is the energy consumed directly, and this is the energy fed into the grid. The energy saving from direct consumption is this value. Okay, so that means that we will have about $780 per year. The energy credits for feeding energy back to the grid, which is 4,300 kilowatt hour, is about $525 per year. Okay, so the total is about $1,300 per year. This is the benefit from the energy produced for this 6 kilowatt PV plants with net metering. The last question is to calculate the payback period for the system based on the saving and total cost. This is the so-called the KPI, the performance indicator to make, for example, the so-called the buyback period. Okay, so the buyback period is of course the time that the installation will take for the profit to equal the investment amount, because the investment amount we have already calculated this value. Okay, for the period payback period is generally equal the total system cost. The total system cost is this one. Okay, about $6,200 divided by the annual saving. Annual saving is this value. Okay, so the result will be 6,000 or 6,200. Okay, yes, 6,200. 200 is missing in this calculation. You can correct this value. Divided by the annual saving, it gives about 4.7 years. Okay, so we can return the annual or the first investment of this PV system in about if you want 5 years. Okay, in 5 years we can pay based on the produced energy the first investment of this installation. Okay, so in this exercise we have talked about a lot of questions about designing, about the definition of each part, about the calculation of KPI, performance indicator of the PV system. If you have any question, feel free to put your comments on this video.